This question is about a box in some kind of chamber where it can slide back and forth, bouncing against two different springs. It's frictionless here, so you can imagine it bouncing back and forth. This would be maybe like an air hockey table, say. There's two springs, one on the left, one on the right. They have spring constants. And the beginning of, so it has a mass here. And it moves back and forth. The box is initially pressed against the stronger spring. So initially, so the spring has an equilibrium point right there, and it's initially pushed against that, compressing. So I'm going to put I for initial situation here. And it has squished the spring delta x. There's a change. If that was x naught, x final, there's the delta x. So, and then after it's released, you could imagine it sliding across to be in the middle where it's not squishing any springs, and then you can imagine it squishing this weaker spring. So it's going to go from here, it's going to launch, slide across to here, slam into this one, squishing this one, and the question is, given that it squished this one on the left so much, and given its spring strength, how much is it going to squish this one on the right, given its spring strength? So this is a question mark there. We know the strength of the springs, and we know how much it's squished here. Well, it moves across like this, and this is a situation where we can use energy arguments. We know by conservation of energy, the change in energy is going to be 0. So that means the energy initially is equal to the energy finally. So it's initially here, it's finally here. Oh, initial, I should say final minus initial is better. Final minus initial 0, what this means is that the energy finally is equal to the energy initial. The point is the energy doesn't change at any of these three spots. If I was to make a note here, when you're completely squished, you have maximum spring energy, and you have 0 kinetic energy. Kinetic energy is 0. Here you have maximum kinetic energy. Your spring energy is 0. And here, after you've squished it all the way, there's no kinetic energy. Your kinetic energy is 0, and you have energy in a spring, once again. We can skip, in energy arguments, we can skip the intermediate phases. This could go over a hill, it could do something wacky, but conservation of energy says the energy you end up with is the same as the energy you started with. The difference is 0. So we can look here and compare. There's no kinetic energy at either of the endpoints. It's not moving at the moment it completely compresses the spring. So what we have is an equivalence between the energy levels of these, the energy within the springs at either end. Energy of a spring, 1/2 k x, or I can, in this situation, say delta x squared. It's how much they're squished. This one, you might argue, is squished in the negative direction. This one's in the positive direction. Doesn't matter, it's squared. These two energies are going to be the same. The K's are going to change, so the how much they squish is going to change. You can just create a straight equivalence there due to conservation of energy.